yang di waiting room. Oh iya. Dia di approve aja. Iya. Ya. Siapa? Udah. Dia belum pakai belum. Ya, minta aja. Iya, registrasi. Ada image. Tapi udah ada yang daftar sih, Bu. Udah ada yang diwajibkan tuh kuliah. Iya, ya, ya.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Okay, a very good morning, everyone, and also to all distinguished guests, speakers, and participants. Welcome to webinar SAPPK, hosted by Building Technology Research Group, School of Architecture, Planning and Policy Development Institute Teknologi Bandung. My name is Fauzan Alfi Agirahman, and I will be your host and also moderator for today's webinar. And we have a quite exciting agenda for today. Can you share next? So this is for our webinar agenda. We will have two sessions with 4 speakers covering the topics that we are discussing today, which is, let's see, the theme for today's webinar is Building the Future from Nature to Architecture in Resilient Timber Construction. So we have 4 speakers for today. Will be spread in 2 sessions. But before that, we will have remarks from our Vice Dean for Resource Management of SAPPK ITB, Dr. Alice Nurnidi. To Dr. Alice, the time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good morning and warm greetings to all participants. On behalf of the School of Architecture, Planning and Policy Development at Institut Teknologi Bandung, I'm honored to welcome you to today's webinar about building the future from nature to architecture in resilient timber construction. This event brings together an exceptional panel of experts. Thank you for Professor Satoru Yamashiro, Dr. Hafsah Salamah, Dr. Eka Mulia Alamsyah, Dr. Rahmat Fritanto, and Dr. Fauzan as moderator. And we also thank you for Professor Suryamanto as head of Building and Environment Technology Research Group for arranging today's webinar, whose work exemplifies the synergy between nature, technology, and architectural resiliency. At SAPPD ITB, our vision is to foster humanistic and agile approaches in architecture and planning, where innovation is deeply rooted in empathy, sustainability, and adaptability. Timber, as a renewable and culturally resonant material, offers a compelling pathway towards resilient and regenerative design. It reflects not only our commitment to ecological stewardship, but also our belief in architecture that respond to human needs and environmental contexts with grace and intelligence. We hope this webinar will inspire new collaboration, deepen our understanding, and sparks ideas that shape a future where architecture grows in harmony with nature. Thank you for joining us, and I wish you a fruitful and engaging discussion today. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much to Dr. Alice Nurdini for insightful and inspiring opening remarks. And then next, to give us a deeper understanding of the vision and the work behind today's event, we would like to invite the head of Building Technology Research Group, to Professor Suryamanto Wonoraharjo. The floor is yours.
May I see? Thank you, Pak Fauzan. Distinguished Vice Dean of SAPPK, Dr. Alice Nurdini, our esteemed speakers, Professor Satoru Yamashiro from the Department of Architecture at Shibaura Institute of Technology in Tokyo, Ibu Dr. Hafsah Salamah from ITB, Bapak Eka Mulia Alamsyah, PhD from ITB, and Bapak Rahmat Fitranto Aditra, PhD from ITB. Ladies and gentlemen, both here at ITB and through the Zoom platform, good morning and warm greeting to you all. It is my pleasure to welcome you to this SAPPK webinar hosted by the Building Technology Research Group under the theme Building the Future from Nature to Architecture and Resilient Timber Construction. Why do we place timber in the center of our discussion today? Timber, in both a natural form and engineered form, represents the promising material for the future of our built environment. It is natural product that function as a global carbon sink. When managed responsibility, timber is renewable, sustainable, and environmentally friendly. It harmonizes with both nature and humanity. Yet the use of timber in building construction presents significant challenges, such as seismic resilience, weakness to fire, susceptibility to moisture and decay, construction methodologies, regulatory support, and even the question of social acceptance. Addressing these challenges requires interdisciplinary collaboration spanning forestry, technology, material science, civil engineering, architecture, and etc. The potential of developing of timber construction industry in Indonesia is highly promising. It can generate substantial economic growth, create employment opportunities, and simultaneously improve the quality of our environment. This is a collective effort, one that calls for cooperation and synergy across disciplines and sectors. Through this webinar, let us explore the diverse dimension of timber construction, from sustainable forest management, material processing, to its application in construction, and finally, the prospect of urban mass timber. I extend my deepest thanks to our distinguished speaker today for this presence and contribution. I wish all participants a fruitful and inspiring session. Once again, thank you very much and good morning. Thank you, Pak Wasan. I back to you.
Thank you, Professor Suremanto, for setting up the stage for today's webinar. Okay, so before we start our first session, so just a few housekeeping notes. Can you set to the next? So we have a webinar code of conduct that we need to follow for all participants. So first, please, participants are required to use a Zoom account with their real name. So don't forget to change to your real names as submitted during registration. And then it is anticipated that participants will maintain order during the webinar and turn off their microphones unless the moderator or MC invites them to speak. Then participants are required to understand and follow the procedure for asking questions, such as participants can ask questions to the speakers after being invited by the moderator using two methods: raise hand and chat features on Zoom and also on YouTube chat platforms. Second, participants can write their questions directly in the chat box using the following format: participants' institution, speaker being addressed, and the question itself. Third, chat can be written directly before the Q&A session or during the speaker's presentation. The moderator will select relevant questions from the chat box and read them back to the speakers. During the discussion session, use the raise hand feature to ask questions directly to the speakers after their name are called and invited by the moderator to speak. The discussion session is only used for substantive questions related to the webinar theme. Later, participants are requested to fill out the attendance list provided by the committee, and the organizing committee reserves the right to remove participants who do not follow the rules. So please, to all participants, to obey these rules. And then I would like to introduce our speakers for today's webinar. So as I mentioned previously, we have 4 speakers. The first one is Professor Satoru Yamashiro from Shibara Institute of Technology, Japan. He is joining us via Zoom. And second, I would like to invite Dr. Hafsah Salamah, STMT PhD, to come in to join in the front of our stage. Third, we have Dr. Eka Mulia Alamsyah from ITB, who also, I think, joining from Zoom also, if I'm not mistaken. And the last one is Dr. Rahmat Fitanto Aditra, STMT PhD, also joining as the 4th speaker. Okay, now, ladies and gentlemen, let us begin with the first presentation session. It is my great honor to introduce our first speaker from Japan, Professor Satoru Yamashiro. Professor Yamashiro will be presenting on a very important global trend, the rise of urban mass timber, Japan's role in the Pacific Rim. Professor Sato Yamashiro is a professor in the Department of Architecture at Shibara Institute of Technology, and he is also a principal architect at Building Landscape, which he co-founded in 2002. His work focused on the design and management of buildings and landscapes, as well as various research and development projects related to urban design. Yamashiro research at Shibara Institute of Technology explores solutions to societal issues in cities, regions, and disaster recovery through architectural projects. He specialized in medium to large-scale wooden architecture, with a particular focus on construction methods and spatial design in urban environment. Professor Yamashiro, we are very excited to hear your presentation. Please, the screen is yours.
Yeah, thank you very much. So it's my great honor to be here. So last month in August, I visit Indonesia, some university like IPB, ITB, and the UGM. So I had a very nice conversation together with the researchers and the professors there. So I would like to start my presentation. Okay. It's okay. Can I start? Okay.
Yes, please.
Okay, so yeah, I read today's title is The Rise of the Urban Mass Timber, Japan Role in Pacific Rim. So as I introduced, I'm a professor of School of Architecture, Shibari Institute of Technology, and the director of the Research Center for Sustainable Building Engineering, Shibaura. So this is a picture of one forest in Japan, Kochi area. So today, Japanese forest is full of timbers, trees. But if you visit Japan, this is one picture from the central Tokyo. It's full of the, you can say, buildings, but still you cannot see any big timber building. You cannot find a timber building from this picture. Probably the buildings are constructed with steel and concrete. So this is another picture in Osaka. Even you can see the traditional castle, but this castle also constructed with concrete after the demolition. They reconstruct the castle with concrete and steel. So my role is I'm a practicing architect and a professor, but I'm a member of some committee to promote mass timber in Japan. As far as Japan is one of the most forested countries in the industrialized world. The forest rate is around 67%. Two-thirds of our land is covered with forest. This is the chart to show the forest rate. Japan, like this, and in Indonesia, almost half of your land was covered with forest, I saw. One of the reasons we have much forest, but we didn't have so much modern architecture, modern building with timber. The reason is Japan is a country prone to natural disasters. So this is the picture after Kanto Great Earthquakes in 1923. Around 100,000 people died with this earthquake. 90% of the people was killed by a great fire after earthquake. So, and we had a great bombing also In 1944 and 45, another 100,000 people died by this bombing, and the city was burned out. And even during the reconstruction from the damage of the World War II, we still have many natural disasters, not only earthquake, but also typhoon. One of the biggest one is happened in 1959, Isewan typhoon. So we established the modern building standard after World War II, but after the Isewan typhoon, we made a resolution on building disaster prevention in 1959. So we call it prohibition of the wooden construction, especially for the public buildings. So it is we reconstruct the cities as I showed you before. The city was full of buildings with concrete and concrete and steel. But even after the resolution, researchers and the architects and the government people continued their effort to progress our technology in earthquake-proof and fire-proof technologies. So, and today we established a new act in 2010 and 2021, the act to promote the use of the wood for the public building also. So my aim is how to rebuild those buildings with timber. So, and I would like to propose or invite to establish Pacific Rim Urban Mass Timber Network between Indonesia, Japan, and other countries on the Pacific Rim area. From now, I would like to introduce some examples mass timber buildings projects in Japan. So this is Takuma building, designed and constructed by Takenaka Corporation in 2020. It is a 6-story high office building. So it's constructed with timber and steel structure together. They use a very special technology for the fireproof mass timber construction. This is the section of the column. The central timber structure was protected by mortar or sometimes gypsum bar. It absorbed the heat of the fires. So this is another example for the fireproof beam. So this is another example, Takaso Woodcraft Building, designed and constructed by Shelter Corporation. It's a 7-story high office building in front of Sendai Station. The main structure was constructed with timber, and there's a section of the column. So in the center, it has a timber column and a gypsum board around the column protect the structure from the fire. So this is the interior of the office. So, and Obayashi Corporation, a big construction company, design and construct 11-story high office building in Yokohama, in the very center of the urban condition. This is a kind of a training center for the company itself, and it hosts many meeting rooms and a hostel room for the guests to join the seminar. So it has a very unique structure, cross-shape structure, joint on site. So this is one picture from the manufacturing the structural timbers. You can see the people, so you can imagine how big the column and the beams are. This is one picture from the construction. It's very unique construction method. It's very different from traditional timber construction, more efficient by steel, how can I say, construction, I think. So this column also covered with gypsum board to absorb the heat from the great fire. So this is the interior of the office. If you come to Tokyo and Yokohama, you can visit at least at the bottom of this building. It's very impressive, I think. So, and now another new headquarter office for Tokyo Marine Company was started to build. The building was designed by Renzo Piano, Italian maestro architect. And it has 20 stories and 100-meter high. This is a rendering. It will open in 2028, 3 years later. So it faces to the Tokyo Imperial Palace and very close to Tokyo Station. So if after this construction finished, people will be surprised and will have a great impact. This building will give a very great impact to our society, I think. From now, I would like to introduce one of my projects. Just finished construction last year in Osaka. The name of the building is Riverwood Osaka-jo Castle. It has 8-story floor and 28-meter high. You can see the white part in the center of this picture. So this is a view from Osaka-jo Castle. You can see the condition of the site. This is a picture after the construction. So this is a picture during the construction. You can see timber structure. This is the model. I said that it had 8-story, but the bottom 3-story structure was constructed with steel, and another 5-story timber structure on top. So this is the structural diagram. So this is a picture after the completion. So to protect the structure from the fire, most of the structure was covered by gypsum board. And we introduced another new technology, flame retardant treated LVL, also to protect this structure from the fire. Some chemical treated timber can absorb the heat, and it can protect the fire from the structure. It can protect structure from fire. So we made many tests with chimney. So we use CLT as a seismic element. We made many joint tests to calculate the number of the pins. So there's one picture from the construction. You can see the very massive column and the beams everywhere. So we use, how can I say, steel panel to joint, how can I say, to joint beam and the column and the bracing together. And to protect the structure from the fire, basically we cover column and the beam and the floor with gypsum board to protect the structure from fire. But as you can see, the bracing and the seismic element panel can be exposed to the interior. So we decide to expose such a big structural element like a bracing to the interior. So this is the picture after the completion. So, and you can see the structural element through the windows. So this is a picture from interior. So a very massive K-shape bracing is exposed to the interior. So it gives a very new impression to the new mass timber construction. So beam and the column are covered with gypsum board. And to use the CLT panel as a seismic element, we connect the CLT panel to the beams with steel plate. So this is the room for the owner. So very symbolic column was protect from fire with chemical treated LVL. This is a view from owner's room to the castle park. So I think it could give realize the very new, how can I say, new standard for the mass timber housing construction with modern technology, I think. So together, during I design and construct the mass timber housing, I collaborate together with governmental research faculty facilities to produce the prototype of mid-scale building same time. Of course, some people and some company continuing to develop the higher mass timber as much as possible. But my interest is not only to realize as big as possible, but to promote the middle scale building for the society. This is a three-story high office building model. So this is the structural rendering. So we introduce plywood panel as a seismic element. So basically, most of the column and the wall can be protected with gypsum board from the fire. And we designed another 4-story high model also. It has a more open feeling, and the seismic element is not the how can I say plate, but this big bracing work as a seismic element. So it will be more open feeling, and so it will be used in many different arrangement according to the different arrangement of the office layout. So, and to promote this kind of medium and large scale wooden construction, I'm a member of the organizing team of portal site website to share the knowledge. I'm sorry, all the information is in Japanese, and it's mainly related to Japanese method. But I hope you visit this site to see what happened in Japan. So, and I produce many video also to share the knowledge and what happened in the mass timber construction in Japan. I hope you visit YouTube website too. So as I mentioned, I would like to promote as much as mass timber construction in this modern city. So, and also not only I would like to work in Japan, but would like to establish a Pacific Rim urban mass timber network. Not only Japan, but with you, Indonesia, and some other countries like New Zealand, maybe west coast of the United States or other Asian country, of course, because those areas are earthquake-prone area, and where seismic resilience is very critical. And the high-density city requiring the high fire resistance. And the high temperature and the high humidity environment where durability, including termite resistance, is very crucial. And the Dutch condition is very different from Europe, I think. Of course, we would like to learn many things from Europe or North America, but then the research and the development of urban wood construction technologies focusing on the Pacific Rim area, Pacific Rim condition is very important. So I would like to keep this kind of, how can I say, conversation and collaboration together with you all. Thank you very much.
Thank you very much, Professor Yamashiro, for your presentation. Can you give rounds of applause? Okay.
Thank you. Thank you very much.
Okay, so it was really inspiring to see the stunning examples of mass timber projects across Japan. And your point to the fire-resistant duration of mass timber is particularly crucial, as it directly challenged one of the most common misconceptions about using wood in large-scale construction. And it's clearly demonstrate how Japan provides a powerful blueprint on how we in the Pacific Rim can embrace this sustainable and innovative building method. So once again, thank you very much, Professor. And now, next, we move on to the second speaker. So to our audience and participants in Zoom and also here in our seminar room, please keep the question coming to the chat box for both Professor Yamashiro and for our next speaker. I would like to introduce Ibu Hafsah Salamah, STMT PhD. Her presentation will explore the intersection of heritage and innovation in her talk titled Technology in Traditionality, Development of Prefabricated Traditional Joints and Simulation. So I would like to read her CV. So Ibu Salamah, PhD, is a lecturer in Building Technology Research Group, SAPPK ITB. She obtained her PhD in Architecture and Architectural Engineering from Seoul National University. Her expertise is about building structures, especially on timber structure and performances. Her research interest is about traditional buildings and joints, and also her past project is about performance of Korean traditional timber joints and rumah gadang structure. To Ibu Hafsah Salamah, the time is yours.
Okay. Thank you so much, Dr. Fauzan. Today's presentation, I will talk about technology in traditionality, development of prefabricated traditional joints and simulations. Actually, this is combined between my dissertation and my current research about prefabricated traditional joints. Okay, research background. So why I choose this topic? This is because traditional timber joints are important for supporting the rigidity of traditional buildings against gravity and lateral loads. And studying traditional timber joints contributes to understanding the behavior and performance of traditional joinery techniques and how to preserve traditional buildings. And two studies are currently explored. The first one is the how to analyze the performance of traditional joint system. And the second one is fabrication on traditional joint using CNC milling. The conventional connection performance analysis from timber standards is only regulate about the dual type connection, which is using metal material. And connection performance that can be calculated is from load carrying capacity, which based on the failure modes happens in two types of connection. There are single shear connection and double shear connection. And limited to this, the calculation is based on the failure modes that happens from the many iteration of traditional joints, and the goal is to find the capacity before the connection damage. And when we calculated the load carrying capacity, we found that between two popular standards, which is National Design Specification from America and Eurocode from European countries, that the NDS standard is more conservative than Eurocode standards. And from this formula, we can find that how the performance of the connection in vertical direction and also lateral direction. But it will depends on also from the adjustment factors that's based on the what kind of purpose of this simulation and calculation. And I also make validation using numerical analysis, and the load for simulation in finite element modeling are adjusted to the load carrying capacity from NDS and Eurocode calculation. And from both calculation is showing that the bigger bolt size on timber connection increase the load resistance, but in contrary, wider failure surface occur in the timber members. So as we know, because the bigger dowels usually make a higher resistance of connection, but because of a high capacity of the metal than the timber, usually the timber occur damage first, then the connection itself. So as we can see the failure distribution, so more bigger dowels create more damage in the timber members than the dowel itself. Okay. So I also check the analytical analysis from the mortise tandem joint that I choose to analyze. This is based on Taiwu model and Norris model, which is usually used in orthotopic material that have multi-directional strength and stiffness. And in here is also convergence with the result from numerical analysis that usually the beam members are the more likely to fail than column members. Yeah, which is convergence with the calculation. And I also analyze the traditional timber joints using parametric study, and I choose 14 joints to be checked whether the performance of each joint and which one is which has bigger capacity than the others. And I also categorize the joints based on the capability of resisting the force, which is I divided into two types, the tension joints and compression joints. The dimension, limit, and proportion of the model size is from National Research Institute of Cultural Heritage in Korea. So basically, why I choose Korea, because my PhD in there also, and several type of joint also similar with within Indonesia. So I choose that one because of that. And the model setup in the numerical analysis is like in the figure left side. So and then the material properties also determined within the material library in the software. And the result is also satisfied that the movement of the joint when we add the tension force, it's similar to the actual experiment or test. And here is some of the results. Actually, I have all of 14 joints, but I only mention in here only three. And how we know that it is the model is correct or not is based on the prediction of deformation and contact behavior. And this is I formulated based on the previous studies and also how the movement of the connection itself. So here we have the diagonal friction and compression, and then we have full compression, and then we have full friction. And from this, we know that what happened in each connection. So after we did the experiment, the simulation, there are found that several behavior and performance of each connection, it can be divided into new categories. Based on the shape behavior, we have hook type joints and locking type joints. The hook type joints have the characteristic that have the same shape between male and female members. And then they have good performance when they have long joint area, and then good resisting on tension loads. and usually the surface contact less than 7. And then for the locking type joints, the characteristic is have different shape between male and female members. And then they have usually short joint area that shorter joint area will have better performance. And then good at resisting compression loads. And then the surface contacts usually more than 5. And based on the tension behavior, it is divided into 2 type of joints, the friction type joint and bearing type joint. So the characteristic is in the friction type joints, the joint is relying on the friction surface. And because of that, additional dose have a significant impact on the strength and stiffness of the joints. And in the contrary, in the bearing type joints, the connection itself depend on the surface that bear against each other and mainly rely on the compression strength. So additional dowels only serve to prevent pull out rather than prevent the connection is become failed. And after creating how to analyze the traditional connection, I want also to move into the how to make the traditional joints become more easier and can be prefabricated in the future. So the background study of the traditional digital fabrication in traditional joints is I mentioned only 2 in here. Kanazaki and Tanaka research about the patterns of traditional joints to be developed in in digital fabrication environment, which is CNC milling. And then the Larson et al. 2020 create the system to make the Japanese traditional connection to be fabricated using CNC milling. And fabricability, durability, and friction and contact area considered as a new metrics in joint fabrication. And here is the example of the picture. What is the goals of the prefabrication is to make the shape that impossible to make by the craftsman. So maybe if you can see, you can the rounded shape is kind of hard to make it manually, but it can be achieved in the digital fabrication. And the ground theory of traditional joint fabrication is that connectivity, bridging, milling direction, checkerboard, sideability, durability, contact area, and friction area. But right now, most of the factory usually already using this kind of approach, but it is limited to mass production. So in my research, the goal is to how to make the traditional joints to become more diverse and explored more than just the traditional ones that we already know. And this is the preliminary prototyping in digital fabrication of traditional joints. So in our building, we have this CNC milling machine, but we still develop the method and the procedure to make it more effective and efficient. And here is the prototype, the first prototype, which is not finished yet and still being developed. But the goal is to make the traditional joints can be fabricated. Oh, okay. So the further research goals that I want to achieve, the first one is the development of traditional timber joint fabrication system based on the machine capabilities and efficiency. And then the formulation of traditional timber joint performance analysis for preservation and conservation of traditional buildings. And then study of strengthening method of traditional timber buildings in Indonesia and how to apply them. And then structural investigation on traditional timber structure to understand Indonesian traditional building under lateral roads, which is still a lack of development right now. And then exploration of more natural material for building structure to reduce carbon footprint in construction field. And exploration of folded plate structure using timber material, which is actually my thesis in my master's degree. And this is all of these research goals is based on the SDGs and our building technology research group roadmap. Okay, thank you very much.
Okay, thank you very much, Dr. Hafsah, for your presentations. So it is really interesting to see how the advanced tools like performance simulation and also digital fabrication can be used to understand and preserve the deep wisdom of the traditional timber joinery. So thank you once again for sharing your work. So now we will continue to the Q&A session for the first session. Uh, so we will begin the first 20-minute Q&A session. I would like to invite both Professor Yamashiro and also Dr. Hafsa. And we have received a number of questions from the audience. Yeah. Okay, so we have the first question from Rijaluddin for Professor Satoru Yamashiro. The question is regarding construction costs. Could you share the current difference in cost between wooden and concrete structures in Japan? Roughly, what percentage cheaper is wood compared to concrete when considering materials and construction?
Okay. Thank you for your question. So actually, the modern mass timber construction is more expensive compared to how can I say concrete structure. But today, around 5 or 10%. How can I say expensive compared to moderate, how can I say, popular concrete construction. So, but as maybe I don't know the situation in Indonesia, but in Japan, the cost for concrete construction and the steel construction getting steeply expensive, getting expensive. So, and the cost for the mass timber can, how can I say, be equal in near future, I think. And how can I say, in Japan, we have two standard for fire irrigation. So one is fireproof Japanese fireproof standard, and also Japanese quasi semi fireproof standard. So the semi fireproof standard fit to the we can say lower building, like a 3-story high or a 4-story high. So I think even today, such a semi fireproof standard cost mass timber construction is more almost equal to the other structure or steel structure or concrete construction. So in near future, the balance will be, I can say, change, and the mass timber construction can be equal or cheaper than concrete, I think. Okay.
Okay, thank you, Professor Yamashiro. Maybe from Rijal, do you have any comments or anything to say? Okay, thank you. We can go to the next questions. Okay, another question for Professor Yamashiro, now from Fibria. What do you think about the obstacles to rejuvenating trees that have been cut down? And what do you think about its application in tropical countries, with the obstacle of minimal heat transfer being blocked by wood? Okay, please, Sensei.
Sorry, I didn't ask clearly, but I think minimal. It's not clear what minimal heat transfer is blocked by. I mean, did it talk about the thermal insulation for the building, or how people can touch to the cold thermal mass or not? Makes sense.
Okay, maybe Fibria can give more context to the questions. I saw the, oh yeah, I saw.
I'm sorry, I couldn't clearly understand your question. Sorry.
Okay, you may unmute first, Fibria, to give more context to the questions.
Yeah. Thank you.
Okay. Has to unmute. Okay, if it's I think Fibria is okay. I mean the timber not as good as concrete to block the heat. So yeah.
I think, in my understanding, the timber is good for thermal insulation. So to cut to protect the movement of the heat from one side to another side. So it's more use, but it has a more good character for the thermal insulation, I think. Of course, to make to how can I say for the thermal mass, it's not so good. But to protect the heat movement, timber is more efficient, I think. Right? Okay.
Okay. Thank you, Sensei. Maybe from Fibria, any comments before we continue to the next questions? Okay, while we waiting, I would like to invite questions from the audience here, or maybe from the speakers, from other speakers. Oh, okay. So Dr. Hafsa has some questions to Professor Yamashiro.
Okay, thank you, Professor. Thank you, Pak Fauzan. So I want to ask to Professor Yamashiro. It's really interesting presentation, but the one that I want to ask is about the a fireproof that I read that it is 2 hours and then there are 3 hours maybe. But the one that I learned in Korea back then is when the timber is being burned and already make charring, it was found that in the certain depth, the timber cannot burn more. So I really curious that what is your consideration that you use the gypsum to add more layers to prevent it? Thank you.
Yes, thank you very much. So, and as I said that we have in Japan, we have two level of fireproof standard. One is Japanese fireproof standard, and the second one is quasi semi fireproof standard in Japan. So, and for semi fireproof standard, what you talk the charcoal, how can I say, charcoal, when the timber changed into the charcoal, it give us a kind of protection it can protect the timber from the fire. But I think, but it's not correct. I think the charcoal stop the fire perfect. It continuing, how can I say, burning very slowly, but it anyway don't stop the fire. Make it slow. And it's very efficient when people can get out. It can save the time to people go outside from when during the fire. And but in Japanese fireproof standard, this building have to stand even without the firefighting. It means even the charcoal make it slow, the burning of the timber. It don't stop at the fire at all. So like after one night, building start to collapse. So and it spread I guess a very bad effect to the neighbors, and sometimes even the city block continuing the fire. So we have a very severe fireproof standard. So charcoal effect is not enough for the Japanese fireproof standard. So we need to use how can I say the gypsum board. But I understand that it's not so very good for it's good for fireproof, but okay, so it's not so perfect for the like carbon neutral how can I say things. So we need to develop another kind of technology beside the can I say gypsum board, I think. Okay.
Okay, thank you very much, Professor. Yeah, that's also my consideration that yeah, the charcoal is slowing down, but it might be can achieve the 2 hours fire resistant, yeah, before the collapse. So the one that I know that in the buildings in Norway, Oslo, is that the dimension of the column is very big to what is it, to comprehend with that kind of system. That's why they don't use any gypsum board. But thank you for your insight. It's really interesting.
Thank you very much.
Okay, thank you. We can go to the next questions, maybe. Okay, from Ardiana Muhsin, ITENAS Bandung, to Professor Yamashiro. I read Prof. Koshihara from Tokyo University about timberized Tokyo a couple years ago. Actually, after all Japan modernization in architecture, what is the main purpose of the idea back to timber construction? I guess it is more than just harmonize between nature and buildings. Please, Sensei.
Yeah, thank you very much for your question. So, and I have a very close contact with Professor Koshihara. So I also influenced by him very much. So I'm a member of Timberrise, how can I say, association. So, and we have many reasons to, how can I say, to start mass timber again in Japan. One is harmonization, but we have many, how can I say, economical reason also. And as you know, especially European or American company or investment company is invest money to so-called ESG movement. ethics, environmental, social, how can I say, governance things. So, and we, Japan, also need to attract such a money. And carbon neutral trial is one of the most important aspect of our development in Japan. So to realize the decarbonization or carbon neutral society, mass timber is very, how can I say, focused on today in Japan. I think so.
Okay, thank you, Professor Masuro. Maybe from Ardiana, do you have any comments? You may unmute or give the comments on the chat box. Okay, yeah, okay. Thank you very much. Yeah. Okay, we can go to the next question. So we have roughly 7 minutes for this session. Okay, so from Abiyu Harit Swabani to Professor Yamashiro, I'm interested on how and where the wood used in mass timber construction are sourced. Were they picked from purposely grown forests or from natural wild forests? Thank you.
Yes. Today, it's very rare to cut down the trees from wild forest because most of the wild forest is very, how can I say, it exists in the very deep mountain and difficult to, can I say, access. So most of the timber come from the, how can I say, treated plantation forest. So the most of the timbers, like Japanese cedar or Japanese pine, grown in the, how can I say, なんだ、plantation forest, not from the wild forest. Okay.
Okay, thank you, Sensei. Hopefully, it answer your question, yeah, Abiyu. Okay, is there still any? Oh, one more questions? Yeah, okay, from Dr. Suhendri to Dr. Hafsa. Do you think there should be differences between the shape or form of fabricated and handmade joints? When and where do you think the fabricated joints will be more useful than the traditional joints? Since your presentation show only small scale joints, would it faster and energy efficient to just give it to the carpenter? Okay, please.
Okay, thank you for the question. So, why is it need to be prefabricated? The first one, the carpenter is limited right now. So, to preserve more about the traditional knowledge, it is necessary to adapt technology to preserve even more in the future. And then about the would it be faster and energy efficient? Yes, of course, because the man-made is require more time, more cost, but from the digital fabrication, it will be more efficient in the term of cost, and then the man-made, and in the future it will be right there than focusing on the man-made. But of course, it will be um, reducing the what is it, the preservation of carpenter itself. But right now, to be more to have more solution to prevent of to prevent the disappearing the traditional knowledge, I think it's important to adapt the technology itself into that kind of topics. Is it answering?
Okay, maybe I would like to add on top the questions to Dr. Hafsa. So maybe do you find there is an element of like intangible craftsmanship in that is difficult to capture digitally by the CNC machine, for example? So how do you balance the perfection of the machine itself with the organic nature of the wood material?
Actually, all of the material can be molded or created for to the CNC milling, but the weakness is the CNC milling is using using like round tip of the round tip. So that's why the fabricated joints usually have like a rounded shape of the connection rather than really sturdy, straight edge, something like that. So it still need to be should be develop more about the procedure and what is the limitation of the machine itself.
Okay, yeah, thank you, Dr. Hafsa. Maybe we have 2 more minutes. I see that there is one more questions in the chat box. Or maybe from from the audience. We have one from the audience. Sorry. Yeah.
Baik, terima kasih. Saya mohon maaf datang terlambat setelah kuliah. Baik. Namun saya tidak bisa lancar dengan bahasa Inggris. Apakah pertanyaan boleh dalam bahasa Indonesia? Ya. Ya, saya ingin bertanya kepada Profesor Satoru mengenai sistem struktur steel frame structure with CLT infill wall, begitu. Apakah di Jepang itu sudah mulai banyak digunakan di gedung-gedung gitu? Karena mungkin saja itu sudah mulai digunakan, tetapi tidak terbit di jurnal, begitu. Karena kalau yang saya kaji di jurnal baru satu yang gedung itu yang menggunakan sistem tersebut, begitu. Takutnya terlewat informasinya seperti itu. Baik, terima kasih Profesor Satoru. Demikian dengan Ramli.
Okay, Professor Yamashiro, there's one question from Ramli here. So he asked about the structure system with CLT and infill wall. Sorry, for infill wall, CLT with infill wall. Is it commonly used in Japan right now, or is still just a part of the research? Because when Ramli found in journal, it's only one only in one article only, if I'm mistaken. Only one building mentioned in the in journal that using that kind of system. Maybe Professor Yamashiro can respond to the questions.
Sorry, it is the CLT panel as a systemic element insert into the frame as timber frame.
Yeah.
What part are you talking about? Yes. Yes, it's a very new way of the usage of the CLT. But we have other example like CLT panel inserted into the steel structure. You know, a post and beam was constructed with steel, and the CLT panel insert into the steel frame. We have some such an example already. And our original point is to use CLT within the CLT, timber post and beam. So we need to make a test, experiment to how can I say, to check how it is strong enough. So it's very new usage of the CLT. till now.
Okay, so it's currently it's not a common system.
Yes.
Yeah.
Not common yet, but
Not common yet.
yes.
Yeah. It's still not common yet. Still need to be tested to check the performance. Yeah. Hopefully it answer your question. Okay, so I think we have the Q&A session for this first session. We can conclude the first Q&A session. So thank you very much for Professor Yamashiro and also to Dr. Hafsa for presenting and also answering the questions from the all attendees. Yeah, we can give rounds of applause here.
Thank you very much.
Okay.
I would like to see you in Indonesia or in Japan. Bye. Please contact me. Thank you.
Yes, yeah, we will see you later very soon, Professor Yamashiro. Thank you very much. We go to the second session for this webinar. We have Dr. Eka Mulia Alamsah. Dr. Eka Mulia Alamsah of Eshut M. Ager PhD, focus on forestry technology research. His specific field of interest include the anatomical and physical properties of wood, the application of wood adhesive, such as adhesive strands of fast-growing tropical wood species, wood processing, and wood composites. Throughout his career, Dr. Eka has acquired various professional skills in various agroforestry equipment related to the wood properties. And his topic for today's webinar is wood and wood products as an engineering material. To Dr. Eka, you may begin your presentation.
Okay, thank you, Pak Fauzan. And thank you to SAPPK who already invited me to speak about the wood and wood product as an engineering material. Can you see my PPT?
Yes.
Okay, thank you. Let's begin. Actually, this paperwork already prepared by Dr. Rudy Dungani and me. And in the same time, Dr. Rudy has to go to Cirebon for the lecture in ITB campus. So he promised to cannot attend this webinar, and I replaced him. In this presentation consists 3 chapters. Chapter 1, I would like to talk about the characteristic of wood from the process of growing tree into wood involves biological stage from seed, seedling, fall, tree, and wood. Actually, wood in the international trade varied into 2 types. They are hardwood and softwood. Anatomically, hardwood are porous with special elements, but softwood are non-porous. And hardwoods are plants with broad leaves, called also tropical wood. Softwood are plants needle leaves. In Indonesia, some wood species include the softwood type such as pine, mercury, agathis damara, and so on. And Wood species include to the hardwoods such as Tectona grandis, Palcataria moluccana, and so on. If we see in the transversal surface of the wood, we can see clearly that the wood consists of softwood and hardwood parts. Usually, hardwood darker than softwood because of the position of extractives, generally more resistant to decay, fungi, and insect attack than sapwood, and lower moisture content compared to softwood. Mechanical strength is not necessarily higher than softwood, though durability enhances its long-term strength in surface. More stable than softwood under changing humidity condition. Hardwood can be harder to work with than softwood. Chemically, all wood is composed by cellulose, lignin, hemicellulose, and minor amounts, usually less than 10% of chemical extraneous materials. Variation in the proportion of this component make wood be heavy or light, stiff or flexible, hard or soft, and durability degree. In the fresh wood, some key advantages include fresh wood has natural beauty with unique grain patterns and texture that add warmth and character to any space. High quality fresh wood can be incredibly durable and long lasting, making it great investment for furniture and construction. Wood is a renewable resource, especially when sourced from responsibly managed forests. Highly versatile and can be used in a wide range of applications, construction to furniture. Wood has excellent acoustic properties, which is why it is often used in musical instruments and spaces designed for listening to music. Natural insulating properties helping to maintain comfortable indoor temperature. However, during post-harvested period, timber is prone to fungal and insect attack during storage period as the moisture content is very high. On a freshly cut tree, the moisture content can be anywhere from 13 to 45%. This is called greenwood or green moisture content. By physical and mechanical effects, wood can be degraded. Some occur change in cross-sectional dimension, like swelling and shrinkage. Strength and stiffness decrease as moisture content increase. Durability is affected, and coating can be compromised to cover especially the surface part of the wood. Chemical effect of degradation in wood can be color change, such as yellowing, darkening, or graying. Reduction in pH would become more acidic, decline in strength, elasticity, and dimensional stability. Increased porosity due to cell wall breakdown. Biological effect of degradation in wood is driven by fungi, such brown rot, dry rot, soap rot, and insects, such as termites, beetle, and ants. Their combined effect include loss of structural integrity, discoloration, tunneling, and eventual collapse of wood material. The environmental factors that affect degradation in wood are biological organisms, such fungi and insects, and risk of wetting or permanent contact with water. You can see in the middle of the picture here. Wood is susceptible to attack when the moisture content exceeds 20%. In the chapter 2, I'd like to talk about quality enhancement of wood. Some of the problems when we use wood are not resistant to humidity, and effect of ultraviolet stability. The dimensions are unstable, resistant to fungal, insect, and weathering. The surface is soft. Because of that, we have to improve the quality of wood before we use wood as a products. How to solve these problems? There are many methods. First, using high quality wood. Second, using naturally durable wood. The third, using wood preservative. The fourth, use dry wood. And the last one, use of technology in wood treatment. Especially in the number 5 or the last statement related to the technology in wood treatment, because in the PACs, we can see that the natural wood from the natural forest with the high quality already decrease. You can see by the red line here. On the other hand, since 2000 years, the government support the people of Indonesia to ground tree in the plantation forest. So that until this year, we can see that the wood from plantation forest leading to support or supply wood material to the wood industrial in Indonesia. However, this policy has resulted in the use of wood of lower quality compared to the wood quality from the plantation forest. Because of that, we have to use some method to increase the quality of wood with some technology. First, with wood drying technology. Forest product, especially wood, contain a certain amount of water in them and must be removed because they have a very detrimental effect on their use. The process of removing the water content in forest product material is called wood drying. This common defect in wood drying, such as crook, bow, twist, scarp, collapse, surface checking, internal checking, and internal stresses. Distortion can be the consequence of a number of factors, including variable shrinkage of wood in different directions or at different angles and excessive internal stress. During is an effort to ensure the stability of the size of wood before use. Below the fiber saturation point, change in moisture content can result in swelling shrinkage. On the other hand, if it is dried too close to the environmental water content, the swelling and shrinkage characteristic will be overcome and can even be eliminated. This is some method in the drying technology. First is air drying method. Air drying is a lengthy process. Usually, its board takes 1 inch per 1 year to dry. The lumber is stacked off the ground 15 to 24 inch on sticker, which are placed across the board and in line to each below, and above in between the board to avoid sagging to gain even weight distribution. And the second method is kiln dry method. Kiln dry is a pause but controlled process where humidity and temperature is controlled using steam and fans for drying. The drying process normally takes between 6 to 8 weeks. Because of its fast drying due to high temperatures, the cell collapses quickly rather than slowly as it would with air drying make it unstable. And the second technology is wood preservation. During post-harvest period, timber and bamboos are prone to fungal and insect attack during storage period as the moisture content is very high. The type of insect such as termite, wood borer, the type of fungi such as rotting fungus, softening fungus, stain fungus, and the last one, the type of marine borer, mollusca and crustacea. Among the wood condition, we can see in this table that the wood in a dry environment had many advantages compared to the other wood condition with the less attacked by wood destroying organism. Definitely, wood preservation is chemical treatment and or physical treatment of wood to extend its useful life. In everyday reality, what is meant by wood preservation is the process of inserting chemicals into wood to increase its durability. The purpose of wood conservation is to incorporate preservative into the wood so that continuous layers of treated wood contain sufficient preservative to prevent rot and insect attack. This is some method of the wood preservation. We can see from the simple method to the high technology method. First, we can use the coating method, spraying method, and then dipping method, soaking method, shape displacement method, and diffusion process. The last one is the vacuum pressure method. The method of vacuum pressure is highly recommended for preserving wood that will be used in the construction of bridge, cooling tower, port, and residential building, because the material of preservative can be easily incorporated with the cell of the wood compared to the others method. And chapter 3, I'd like to talk about wood product composite. Technologies for the development of wood product. Natural wood is often subject to cracking, degradation, aging, and dimensional instability, which leads to the reduction in its service lifetime. Wood drying, preservation, and modification are applied to extension of service life, especially in material component of timber or biocomposite CLT and glulam for building application. It is a kind of wood product composite. Definitely, wood product composite are engineered material made by combining wood elements. veneer, strand, or particles with adhesive, resin, or other additives to produce material, enhance strength, durability, stability, and versatility compared to solid wood. You can see here that some wood product composite like LPL, PSL, LSL, OSB, plywood, particle board, and fiberboard. Solid lumber is lumber that has been just cut from a tree, unlike engineered wood, which is composed of wood fibers that are held together with adhesive. Solid lumber contains wood fiber throughout the piece of lumber. Here, plywood. Plywood is widely used in building components because of its unique properties that make it stronger, more stable, and more versatile than solid wood. Strength and stability of wood with the grain direction alternating at 90 degrees. And plywood has also dimensional stability. The main building component made with plywood is structural component such as flooring system, roofing, wall system, beam, and joists. Second is hardwood. Hardwood, also called high-density fiberboard or HDF, is a type of fiberboard which is an engineered wood product. It is used in furniture and in the construction industry. The main building component made with hardwood are wall and ceiling panels, doors, screen, flooring, underlayment, furniture panels, and sometimes exterior siding of tempered wood. And then particle board. Particle board or chipboard is an engineered wood product belonging to the wood-based panels manufactured from wood chips and a synthetic, mostly formaldehyde-based resin or other vegetable binder, which is pressed under a hot press. The main building component made with particle board are wall and ceiling panels, flooring underlayment, door, doors, cabinets, shelving, countertop, and modular furniture. We can see that the comparing among plywood, hardwood, and particle board. Plywood, strong, stable, and available in large sheets, suitable for both structural and decorative purposes. Hardwood, very smooth surface, but dense, used mainly for non-structural component, tempered version for limited exterior use. And the particle board, economical, flat and smooth, but less strong and less moisture resistant, mainly used for the interior function. Next is the laminated vinyl lumber or LVL. LVL is studded composite lumber made from thin wood veneers, bonded together, offering durability and structural support in various applications. The main building components made with LVL, such as beams, girder, headers, rim board, joint, plank column, roof rafters, stringers, and concrete from work panels, like in this picture. And then cross-laminated timber, or CLT, is an engineered wood product consisting of layers of kiln-dried dimension lumber oriented at right angles and then glued to form structural panels. The main building component made with CLT are loaded bearing walls, floor, slab, roof panel, stairs, elevator staircase, and modular building unit. Oriented strand board or ESB is also kind of the wood composite. USB is a versatile engineered wood panel crafted with waterproof heat cure adhesive, featuring rectangular wood strand arranged in cross-oriented layers. The main building component made with OSB are wall and roof, floor, subflooring, joist webs, side panels, and modular building units. And the last one is a hybrid composite. Hybrid wood composite are engineered material made by combining wood, natural fiber finish particle or strand with other materials such as polymer, metals, or different types of wood-based composite to enhance the performance. Laminated bamboo hybrid composite, such as in this picture, using laminated bamboo, strip, and oil palm veneer were produced by arranging the materials in alternative layers. A 5-layer composite from oil palm veneer and bamboo strip at phases was produced by using 2 different arrangements of the layers, in example, perpendicular and parallel. In the parallel arrangement, bamboo strips were placed parallel in each layer. Meanwhile, in the perpendicular arrangement, the bamboo strips were arranged at 90 degrees to each layer. That's all. Thank you very much. Terima kasih.
Okay, thank you very much, Dr. Eka, for your presentation. It's really interesting to have the presentation started with the fundamentals of the wood itself and how the material evolved to become more advanced products like LVL, CLT, and hybrid composites. So it's really interesting to see from the beginning to the advancement of the material itself. So thank you very much, Dr. Eka. And next we go to the final speakers. Dr. Rahmat Fritanto Aditra. He will be presenting on fiber filament winding composite construction. And Rahmat Fritanto Aditra, PhD, is a lecturer at Building Technology Research Group, SAPPK ITB. He earned his PhD from the University of Nottingham, UK. His research and project focus on innovative structure and sustainable materials, including bamboo and tensegrity system, etc. He has been involved in numerous projects, such as designing a bamboo geodesic dome for disaster relief in Lombok in 2018 and the Jute Tower at ITB in 2019. So to Dr. Rahmat, the time is yours.
Okay, thank you, Mr. Dr. Fauzan. First of all, the Judo Tower is last year. Yeah. Okay. Yeah, thank you for giving me the opportunity to present in discussion about timber. Biomass material that I'm familiar with is mostly about bamboo because I'm helping Mr. Andri. But what I will try to explain here something that is, I think, rarely discussed in Indonesia. Just because we have the opportunity to be able to explore it in ITP. So it might be mouthful, but we'll go through it one by one. But this wound doesn't mean it's a wound. Yeah, it's a winding. In Indonesia is menguntai. Yeah, so we'll go through the background, why this research coming from, where is this coming from, then the concept of the fiber filament winding, and the progress that we have been doing up to this point. Okay, next. Yep. Okay, first is the background. So many of my research regarding is various material is concerned about the current construction industry that focus on increasing the efficiency of process of making the buildings, making the component, but less about the material itself, right? So we make a rectangular building because we know it's easier to make. People are easy to understand it. The workers can work it easily, but we all know that for example, to distribute load, it's better to have a efficient form, right? So the building materials are produced to accommodate various use. Thus, the design has to be adjusted according to the available building components, reducing our possibilities, like how we make, if we want to make a steel building, we have to see what is available in the market before we can design it in details. So, and timber, I think, is also doing in that way. Timber are traditionally produced, used, and building in this way, either in form of panel, planks, or beam. This is makes sense. It doesn't mean it's bad because the trees goes in one way anyway. So we have to make use of what's naturally grown. That's why we have to design it based on its anisotropic component, not properties, right? But I've always been wondering, is there any other biomass material that can restore carbon that naturally can be constructed in a flexible way? So allowing as an architect or designer to play with it more flexibly, more flexible. So I'm thinking about fibers, like because it is the building blocks of trees and and plants. It is flexible and it is small. However, many of the construction system that use fiber has to use short fiber in random orientation. For example, GRC, right? We have to mix it. Hemcrete or OSB that we showed before, because it is easier to play with if we cut the fiber first, which is counterproductive to what the fiber is good for. As the longer it is, the stronger it is in tensile. So is there any way to use fiber in long form, like in form of filament, like carbon fiber, or a rope that's already been there? So there is a technology in, there is a fabrication method used in composite industry, which is filament winding. This is where the name comes from. It's a fabrication method which the filament are untie into its position based on its requirement. That is basically how, for example, carbon fiber tube is made. It is tension, dipped, yeah, or impregnated into a resin bath. Then you wound it into its core. That's why they always have a core. This is also the same method, more or less, when we are making wind blade, yeah, blade for wind turbine, yeah, same method. And then in architecture discipline, it's evolved by some institution to make it bigger and less waste, which is by removing the core. So when previously the winding is made by molding a mold, by winding a mold. Right now, what they develop is something like, unfortunately, this is not in ITB yet. This is they still have a frame or some kind of mold, but it is smaller and expand into a bigger, expand at its actual size, so it can make a bigger size, right? If you want to make one by one building with a whole core, you can imagine how difficult and how expensive is that. So they call it coreless fiber winding, even though this is just one of the different method they make, but basically what they aiming for is for making a bigger size and less waste. And the first thing that I found about this technology is we are using carbon fiber, but many institutions already start doing with natural fiber. I think in this building, it's they are using flax or linen. there are many institutions emerge using the natural fiber with in filament winding construction. This too is similar with the carbon fiber method where they use epoxy, not epoxy, I mean resin to hardening it. But there are also research that's using clay to combine it with clay. But when previously clay and fiber are combined with the mix or random orientation of fiber, right now they orient the fiber according to the strength required. So whereas I think it's very efficient and very high in percentage of fiber. Okay, so I want to explore in this research, but reading the article, there's a lot of milestone it needs to be done. For example, oops. For example, the form finding, the physical properties, mechanical properties, and all of it. When I read the journal, they are affecting each other. Different shape will have different mechanical properties. Different mechanical properties of the resin, for example, will affect the fabrication and also the final product in different positive and negative effect. And also the type of fiber that we use also affecting the construction process, fabrication process, and also the result, which also sometimes working against each other. So here I'm quite confused how to start with. So instead, I use an exploratory approach, which start with with the current boundaries that we want. So I narrowed down into material into several things. For example, the material that I'm using, I will start with is jute. Jute in Indonesia is rami or karunggoni. Yeah, it is very common sold in Indonesia, whether it's produced from Indonesia or from India, Bangladesh. Yeah, I think India and Bangladesh and China dominates the market. Also, the arm reach of the robotic arm, which ITB has but it's only 1 meter in reach, without any other system or additional robots or set up to help. And also the end effector, the tools that will spin the fiber. We have no sensor or actuator yet, so the rest of the control needs to be done manually. So we start with that limitation, and we started with prototyping, keeping the problem as narrow as possible first. Fortunately, we have a true opportunity to explore the possibility that we have. First is a jute tower. It is installation that we show in Atria 2024. It's a 3-meter tower installation using a panel of jute fiber integrated with natural glue. Yeah. So the main structure is actually the steel bar, so it has no use of strength at all. So in this case, I'm not thinking about the strength, even its own strength without need to resist any load from the outside. Yeah, and because of that, there's things to improve. For example, the weak tension, because it's not designed to be strong anyway. The fiber is not tensioned well, because of its flat surface, because it's flat, and the resin is not strong enough for such thin panel. Is very easily bent. Then low impregnation resin. In the 2004, we are using one rope passing through the resin in this range. So in many cases, because we have to hasten the wounding, the resin doesn't really stick into the rope. So we start with this to improve in the next installation. So in the next installation, we try to have some aim. What is actually we are trying to make here. So the closest application that we are aiming for is a secondary skin, because to make something structural, there's a lot of mechanical properties and mechanical simulation that has to be done. So we skip that one and focus for, at very least, its own shape first. The customization, which the fiber filament winding can be used for, is to customize the density of the winding, which could customize the transparency as a secondary skin is used for. This is the example of one building actually use it. It's the same institute that developed this research. This is using a carbon fiber. So first we start. So I'm trying to find what form active shape that can be used. I'm going for a saddle shape or hyperbolic paraboloid. This is the image of it in the membrane. This is very simple shape, but it has a two axis of mesh, two axis mesh that works in two direction. The question is how to make this kind of mesh with just one rope. It's basically connecting ropes, right? So I try to use a mock-up first. So with my hand, with a rope, I try to find the concept, and we found a simple and symmetric shape. So it's basically symmetric in four quadrant, and all is so the direction is from here, 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 here. Yeah. So it's very simple. It's reducing the risk of loose section in several places. If this shape is to be lengthened in one direction, for example, there might a chance that several areas are not touching each other between the wire. And also, this is a very simple script to adjust the density. So as I said before, if this is to be used conceptually as a secondary skin, we can simply adjust the density or the translucency by skipping some nodes. For example, this is without any nodes skipped. This is 2 nodes skipped, and this is 4 nodes skipped. Depend on the initial density, we can reduce it very very flexible. So because this is a very sensitive fabrication method, we have to simulate from design to the fabrication, because the design itself affecting the fabrication. So through the script, we simulate the dimension, the simplified model for the aesthetic purpose, winding path, which is the direction of the robots, and the robot kinematic simulation, which define is that winding path possible for that robot. So here we test the maximum size that we can do, the achievable curvature that we can do, and also the number of dowels. So we also update a little bit in the fabrication. So first, previously, as I mentioned before, I used 1 rope, but this one I use 4 ropes, but with smaller ropes. With that, we are able to mix it with the resin better, because it's 4 strand going out, passing through the resin. So more surface area to contact with the resin. This is also actually good for structural purpose. Unlike my intuition, turns out for this technology, for this structure, a straight fiber is better than a spooled rope, because in the final product is not only for tension, but is also for compression. So having a straight fibers in parallel with the direction of the filament is better. So by using a smaller strand that is combined without any rotation, without any spooling, is actually better. This is also what is done in the different institution. We also using a better frame and joinery, strong enough to resist pretension during the construction. Because of the shape, just like a membrane, the frame is pulled inwards during the construction, when the resin is still wet. So we have to have a strong frame, and this frame is made from 3D printed plastic. Why? Because the shape is irregular. The shape is quite strange. So we are able to build it, and it can hold its shape by themselves. So compared to the previous one, the frame is smaller. So it's only this three steel bar, and in some places they can be extended to themselves. They can hold to themselves like this. And also this frame is now in our basement, and I already tried to cut some of the frame, removing the frame from its place. And what we found is that the pretension not significantly decreased. I can't even say there is no pretension anymore once it is dry. So we don't really need that strong frame once it's dry. So maybe in the next step, we need to separate between frame, which will be there in the final product, and the molding that is at very least stay in place when it's still drying. Then hopefully we can have something that right now the frame is quite thick, dominating the whole installation, right? Even though the aim is for having something very light. So the next one is the precision. Maybe you can see it here compared to the simulation that they make before. This is very hollow, I would say, very translucent. The number of the fiber is very sparse. It's because we only can reduce the distance of the dowel 4 centimeters. Previously, it's 6. We reduce it to 4 centimeters between dowels, and that's already colliding frequently because we are using plastic end effector. We 3D print it, so it's very loose. In some way, it helps because when it collides, it can move by itself, but it's less precise, not allowing us to make a very even denser dowel. So the next step will be to make a more reliable setup for the table and effector, which right now we have to make it ourselves, which is not very strong. So the conclusion that what we learned from these two projects up until now, if there's a clear boundary and limitation on what we can make anyway, might as well limit the problem to that boundary, because up until now, at very least, this shape doesn't really require sensor or actuator, because we don't during winding this shape, we don't really need to pull the wire, the fibers, or we don't really need to measure the tensile at this point, and the shape is still fine. So if there is a clear boundary, might as well limit to that problem, and you might not need to you can skip some of the problem. Then this result is also show there is a potential to use natural fiber with fiber filament winding fabrication method. And the last thing, I think many people when shown this research always think about the automation, but actually compared to the already developed research, what we built here is very simple. We don't have any sensor or additional actuator. The robot is only to make the position, and you can always do that in manually. So at the end, we can always alter the rate of automation that we want. The next milestone that we will do is to make something bigger, the design and the fabrication that is bigger, something like this, and to test the physical properties, for example, the toxicity and also the durability. Because right now I'm still using epoxy resin, and also which I know is not good against sunlight. You have to add additive, which still only has limit to 10 years, if I'm not mistaken. And the last one, this will be the last because it's the most difficult, I think, is the mechanical properties to shift into the structural component. I think that's all from me. Thank you.
Thank you very much, Dr. Rahmat. That was a really interesting explanation on how you see completely different way of thinking about buildings. And it's not just necessarily the material itself, but you are going back to the fundamental building block, which is the natural fiber. It's really interesting. You explained about the Jute Tower project, which is a year ago, yeah, not 2019, and also the latest one is Jute Skin installation. Okay, so thank you again for sharing that with us. And now we will go to the second Q&A session. So to all participants in Zoom and also here in the seminar room, you may prepare your questions to both Dr. Eka and also Dr. Rahmat. And also don't forget to scan the attendance and feedback form as shown in your screen, where you may eligible to get the e-certificate for this webinar. So you may scan this QR code again. Please fill in the attendance and feedback form using this QR code, and you may eligible to get e-certificate from this webinar. Okay, so we have first question from Asrul. I think this one is for Dr. Eka. In ancient tradition, it's even a collective understanding in traditional communities across the archipelago that wood cut during a full moon is drier, easier to process, and less susceptible to pest. What is your opinion, Dr. Eka, as a forestry expert? Thank you.
Okay, thank you very much, Mr. Asrul, for your question. But however, actually, until now, I never read or heard any text or paper publication that state the cutting wood during a full moon is drier and easier to work. However, in my understanding and my experience, that statement applied into bamboo species. Yeah, many times I heard and read some publication that when we cut bamboo at the full moon, the bamboo characteristic will be drier and easier to work than the other bamboo. Yeah. So as a one of scientists work with wood and bamboo, my answer, the statement is applied for bamboo species, not for wood. Okay, Mr. Asrul?
Okay, maybe Ashok, do you have any comments or response? Okay, thank you. So now we go to the second questions. Yeah, from Nurfianto Giar Pangidung. Question to Dr. Eka. Does the design of a building, which includes wooden components, affect the level of damage from pests like termites? And what are the latest technologies for pest-resistant wood? Thank you. Please,
Thank
Dr.
you.
Eka. Yeah.
Yeah, Mr. Nurfianto, ya.
Yep.
Thank you for your question. I'll try to answer the question. So I agree with you that the wood as a component in building at the same level of damage can be attacked by the microorganism such fungi or termites, but depend on the wood species, of course, because some wood species in Indonesia naturally has good durability compared to the other wood species, such as Jati species or Tectona grandis in the Latin name, and the others, such as camphor wood, compared to maybe Sengon or Jabon or pine wood species. So, but naturally, yeah, wood can be attacked by the biological microorganism. Yeah. And what are the latest technology for pest-resistant wood? While wood has been a renewable and versatile material for centuries, its susceptibility to biotic and abiotic degradation remain challenging. Of course, traditional preservation methods is easier and low cost compared to the modern preservation methods. From the paper publication in the Journal of Bioresource, I find some information that the latest technology in wood preservation, including the nanotechnology and self-emulsifying drug delivery system, or we call as a SEDDS. Full information can you read in the paper published in Journal of Bioresources. Okay, I think that is my answer for your question, Mr. Aprianto.
Okay, thank you, Dr. Eka. Maybe from Nurfianto, do you have any comments? Okay, is there any current technologies specifically for preserving wood from termites?
Actually, the new technology still the best is vacuum pressure soaking, but in the material of preservative, the latest technology convert the material into nano size using nanotechnology and SAP emulsifying drug delivery system, or SEDDS. That's right.
Okay, thank you very much, Dr. Eka, for the response. And I would like to invite questions maybe from the audience here. Okay, okay, from the other speakers, Dr. Hafsah, please.
Thank you, Mr. Dr. Fauzan. So I want to ask to Dr. Rahmat. So it's really interesting type of structure, and I want to know that is it possible to have winding jute in the terms of structural elements? Like how is the capacity, and is it possible to use it as columns or beams, like substitute to timber, steel, or concrete?
Yeah, thank you. The answer is yes, but compared to what is already exist, I don't know yet how far the difference are in if I'm not mistaken, jute is actually not that different from flax in strength. I think the difference in that case, in their case, why they are using flax, because it's the availability. The European has more access to flax, but the example that is done in the Stuttgart, for example, and also in Germany. Yeah, no, it's both Germany. I mean, they are both. They are already using it for arch. Yeah, so like a surface structure, and also they are already. The last slide that I show is already used for long span beam, long span roof. I don't know exactly how long is that, but I think it's much bigger than this one. So it's already been done. It's been used already for. They also have another institution already make it also for a column, but there is no example yet for high multi-story column, for example. But for a floor, long span beam, it's already been done.
Is there any limitation of how heavy is the roof covering is, or?
In my understanding, because it is very flexible anyway, you can always add the layers. So it really depends on how layers do you want. I think the closest limitation is the pretension during the construction. So many of the failures is on the details. So for example, the connection in the joint, many of the problems, not because the flux or not the flux is ruptured, but the lamination. So and that is because each fiber doesn't really pull each other during the construction, during the fabrication, and that is, I think, the I don't know about the numbers, but the main construction structural failure that's happening in this construction.
Okay, thank you. May I also ask Dr. Eka? Okay. So Dr. Eka, I have some what is it? I curious about some theory that say because you mentioned about the hardwood and softwood. I heard that the softwood is better to resist compression strength, and then the hardwood is better to resist tension strength. Is it correct, or is there any explanation in the forestry field, something like that?
Okay, thank you, Dr. Hafsah, for your question. In my opinion, generally, softwood consists by 90% of trachate cell. So we can call that the softwood homogeneous species compared to the hardwood one. But in the characteristic of physics and mechanical, in my opinion, depend on the wood species. In each kind of wood, softwood or hardwood, because the mechanical properties depend on the density of the wood, range from the 0.1 to 0.7. Yeah, in a standard, and divided into 5 class of the strength by PKKI, peraturan kayu konstruksi Indonesian Construction Wood Regulation. the difference of strength depend on how we get the plank of the wood. If we cut the plank from the wood through perpendicular of the rain sail, we can get the quarter sawn wood. And when we test the mechanical properties, this quarter sawn wood better than the flat sawn wood or tangential wood, which get when we cut the fruit in line with the ray cell of the wood. So we cannot say that the softwood better than hardwood or hardwood better than softwood, because the strength depend on the position of the plank and depend on the density of the wood. I think that is my answer, Dr. Hafsah.
Okay, thank you so much, Dr. Eka. Yeah, it's really clear. Thank you.
You're welcome.
Okay, thank you very much, Dr. Hafsah, for the question. I also have a question, I think, for Dr. Rahmat. It's not really about the material itself, but the implication from the works that you have done, where your work involves like robotics, so simulation and digital design. So do you see it as replacing the traditional construction skills, or does it create a new need for a new type of digital craftsman? And what skills should our students be learning today to work with these kind of systems?
Yeah, thank you, Pak Fauzan, Dr. Fauzan. To be replacing or not, I think it's closer, we can call it evolving, because I see it as how I think, I don't know, I just I see the parallels in the technology of laser cutting. During my bachelor degree, laser cutting, I already learned about laser cutting, and I like to explore the design using it. But at that time, many people say that it's not going to be used in Indonesia because the technology is expensive at that time. Now you can find it other side of the road, right? It's available everywhere, and you can see many buildings using aluminum composite panel that is cut by laser cut. I think what's going to happen is every technology will be researched to up to its limit, to the moon. Yeah, it's very high, but we can give it to the society to decide which part they will use. So at very least, robotic arm is not really that rare. You can find it in apa itu for a welding machine in carrossery industry. They are already using that to weld, because they move in the flexible way and repetitive way. So I don't think just for winding it will be difficult. It's not going to be difficult. The question is the remaining sensors. I think that is the difficult part. So that's why I'm starting with something without it. I don't know how. I think what's going to happen is to evolve. Maybe it's not going to replace timber, of course, but how it be, I think it will be used in other form which is similar with what my research is. So for that, what is I want the student to learn, it's not really about the detail of the how you build it. It's more about how they can simplify the problem. Like what we do with the jute skin seems complex, but actually I simplified the problem with just simple shape and also simple parameter, which is removing one dowel every steps. So to simplify a complex problem into something integrated and simple to solve, which everybody can work with. Yeah, I think that's what student needs to learn, because I think in terms of industry, is going to move very fast. For architects student, what they need to learn is to simplify those problems.
So it's not about technical skill, but more into like the thinking itself, the strategic thinking on the approach.
Yeah,
Yep.
I think technical skill is they cannot skip it. They need to learn it. But I think for ITB student is fast. They can learn it very fast. New software, they can learn it very fast. But the problem is to to be able to repeat that outside when they already in the industry.
Okay, thank you. Due to time constraint, we have final questions. This one for Dr. Rahmat from Rijal. Yeah. So, well, great achievement, Dr. Rahmat. As we know, Jute Tower exemplifies how traditional materials can be reimagined through modern technology to create innovative and sustainable architectural solution. During the prototyping process, did any failures occur while using a smart hand or maybe the robotic hand to fabricate the jute tower panels?
Okay, thank you, Mr. Rijal. Um, is there any failures? Fortunately, there is no failures in the robotic arm because that's expensive. But the remaining things, there's a lot. Yeah. I cracked many, not bones, but the 3D printed arm, 3D printed prototype setup. For example, the end effector, I cracked several times. I also changed several times the syringe because the epoxy is stuck in there, and basically all of it because of the collision that I said before, where the precisions matters. Even in that 4 centimeters, which is quite big in terms of fabrication, right? In manufacturing, their error is millimeters. In my case, 4 centimeters is already colliding. Yeah, because I'm using plastic, which after several panels is made, they are already deformed, and I need something that is more robust, like a steel, which is quite expensive. So, yeah, the failure is mostly collisions. Yeah.
Okay, hopefully the answers can be accepted by Rijal yeah, Rijaluddin. Okay. Thank you very much. So thank you to Dr. Eka and Dr. Rahmat. That concludes our final Q&A session. We really appreciate you sharing your deep expertise with us. So, distinguished speakers, ladies and gentlemen, we have now reached the end of our seminar. So again, don't forget, we will have another seminar in October 16th, which will be hosted by the Development Management and Policy Development Research Group with the title Climate Change Adaptation in Coastal Areas. So don't forget to join with a webinar SAPPK later next month in October 16. So now we will go to the photo session. So the first, sorry. So we will have the certificate ceremony first to all speakers here. And we would like to invite Professor Suryamanto, our head of research group, to give the certificate to our speakers here in the seminar room. So the first one is for Dr. Hafsah Salamah. And the second one is for Dr. Rahmat Fitanto Aditra. And the third one, fortunately, is for myself as moderator.
Congratulations.
Okay, for Professor Yamasiro and Dr. Eka, you will also get a certificate from us and will be sent you via online. And before we conclude this webinar, we go to the photo session. Maybe for the first one is for the Zoom attendees first. So can you help Iza so please turn on your camera. So we will make sure that this picture will be part of our history.
Okay. Okay. From the participants in the Zoom meeting, we have Okay. So for the participants in the Zoom meeting, we have 5 pages. So for the first page, please all of oh yeah, okay. So for the first page, 1, 2, 3. Okay, and the second pages, 1, 2, 3. Third pages, 1, 2, 3. Fourth pages, 1, 2, 3. And the last page is 1, 2, 3. Okay, thank you.
Okay, thank you. And now for the photo session for everyone in the seminar room. Oh, atau duduk di sini aja. Tapi sepi apa? Sana itu. Ya. Apa? Oh, sini aja ya, maju aja, benar ya. Karena kelihatan dikit ya. Iya ya. Oke. Silakan bisa maju ke depan. Terima kasih. Thank you very much. Okay, so thank you very much to everyone over Zoom and also here in the seminar room. See you in the webinar next month on October 16. So, selamat siang, good afternoon. Assalamualaikum warahmatullahi
Thank you, Pak
wabarakatuh.
Fauzan. Terima kasih SAPPK.
Ya, sama-sama Pak Eka. Thank you, terima kasih.